Okay, I think, yeah, I think we are live. We can start. So, salam everyone, and welcome to this session of the Morocco HPC webinar series dedicated to HPC. So today we are delighted to host Nicolas Garenesh, who has been head of research support division at Sorbonne Paris North University since 2011, where he oversees a medium-sized computing center supporting a wide range of scientific disciplines. Nicola holds a PhD obtained in 2023, and he is actively involved in bridging the gap between traditional HPC infrastructures and modern cloud environments. So, in this talk, Nicola will guide us through a practical and insightful presentation titled A Cocktail of Tools to Manage an HPC in a Flexible and Automated Way, drawing on his experience managing the heterogeneous Magic cluster featuring on mix of CPU and GPU and the hybrid deployment models, and he will share how tools like kdeploy, Ansible, and LXC are used to streamline the deployment, configuration, and maintenance of HPC environments. So please do not hesitate to ask your questions during the talk. Without further ado, the floor is yours, Nicole.
Thank you, Imad. Thank you for the invitation. Thank you to all our listeners. So we are going to talk about administration of an HPC cluster because in University of Sorbonne Paris North, we have a kind of uncommon bricks of software to manage our HPC cluster. So I'm going to share with you some experience about this software stack. And we will start by presenting the playground. It means that the machine I administer at University of Sorbonne Paris North. So, as Imad said, I work at the research support. I'm the head of the research support, and I'm located at IT department. It means that I don't belong to any laboratory of the university. I'm independent, so I can give the same service to each laboratory of university. And I work on a computer called Maggie. Maggie is a medium or more small-sized HPC cluster. It's about 4,000 cores, and we have 10 800 GPU cards. And we have about 2 terabytes of raw storage on a distributed file system, of course. But what is a bit uncommon about Maggie is that we have a mix of several architectures. This is because we buy a few number of computers during the years, so we have a little bit heterogeneous resources. And we also have a mix of usage. We have people that want to access the HPC cluster directly on SSH on nodes. And we have people that use job scheduler, we use Slurm. And last but not least, I have a mix of users. It means that the users of Maggie come from several fields. They don't have the same requirements. And we can host people that make distributed computing with top-notch libraries and 100% CPU on each process. But we also have people that look for a place to run a single thread process for a vast amount of time. So we have really a lot of different population on Maggie. That's why in the title we talk about flexibility. First, and I'm not going to spend a lot of time on this slide, just to make it clear what is an HPC cluster. An HPC cluster is a distributed system dedicated to experiments, and experiments that cannot be handled in a single computer due to lack of performances. So we have to make several machines work together to solve problems. users connect to something called a front-end node. They can log on this node, compile their software, and access to their files. We have also a backend node, which is used by system administrator to maintain services of the HPC cluster. And last, we have a storage node, which hosts the distributed file system to make users' file accessible around the HPC cluster. And just below, we have two sets of hosts, because on an HPC cluster, you submit your job, you make, when you make a reservation, you make a reservation for a kind of architecture. You don't target explicitly a node. You can do it, but you may wait for a lot of time for your job to run. But you target an architecture and you submit your job to this architecture. So we have different set of homogeneous nodes. So to maintain an HPC cluster, we have four major steps. Sorry. The first step is to deploy nodes. This is what we call bare metal provisioning. You, roughly speaking, you deploy an operating system to the host. And as you can imagine, I don't make computer one by one with my USB key. I have tools. I have a tool to deploy an image on nodes. The second step is post-configuration. When you have deployed this image, you have to set up a lot of things on your computer, the network configuration, the link to the directory where your users are stored, the link with the distributed file system, install some mathematical libraries, install some stuff, monitoring, etc., etc. We have a lot of post-configuration on this image. You also have to make minor upgrade on nodes, because when the node is deployed, as it comes from an image, the package are not up to date, so we have to upgrade it. And that's what I call minor upgrade, because it consists in upgrading some pieces of software, but you don't upgrade the operating system itself. So step 4 is major upgrade. This is when you upgrade the operating system. For example, when you go from one Debian release to the newer one, you make a major upgrade. And in this case, the major upgrade go to step 1, because you redeploy this image. When we talk about provisioning bare metal compute nodes, we first deploy an image, as I said before, and then you deploy user programs on this image. You can have several scenarios. There are 3 main scenarios. The first one is diskless node. In this case, you don't have an hard drive on computers, but all computers mount their operating system at boot time via something called initramfs. Initramfs is a kernel compressed in an archive, and at boot time, this image is retrieved by TFTP from a PXE server, and the system boot with this kernel. As this kernel boot, it mounts the root file system of the operating system from a distributed file system. Most of the time, it's on network NFS, network file system. It's really easy to manage because you don't have to deploy an image on each node, as each node is configured at boot time. But in this configuration, performances are are closely related to the quality of network. If you have a bad network, you will have bad performances. And all your actions are stored in random access memory. So you occupy a lot of RAM with operating system. But this deployment is popular because in Fugaku, the Japanese HPC computer, they work with diskless nodes. But you have to be aware that they will have impact on network performances. The second scenario, and it was the first scenario I followed when I ran Maggie in the beginning, it's a full deployment on disk. It's a bit tricky to maintain because you have to deploy the operating system plus user programs on each node. So you have very large image that you must put on every node. And the consistency of image is hard to maintain because sometimes you update a library on 80% of nodes, but you forgot some nodes because they were down at the time you upgrade the software. So it's very fast in terms of performances because everything is on the hard drive. So with input-output greedy application, it's the most efficient scenario. But you should keep in mind that it's tricky to maintain, especially during upgrade process. And the third scenario is an hybrid scenario where you have operating system on disk and you have programs deployed on network share. It means that your compute node has its own operating system installed on the hard drive. And when you want to install a program on the HPC cluster, you put this program in a distributed file system. And that's how I currently run Maggie. For our hybrid deployments, we have to handle, as I said on the very beginning of the presentation, I have some heterogeneous nodes. So I cannot put a big image because the image is monolithic. When you deploy it, it should fit your CPU architecture. And for me, it's very difficult because I have 6 different CPU architecture. So we only push a base system. If you install a Linux from scratch, you start with minimal tools and the package manager, and that's what I deploy in the beginning on each node. I had to split the base system and the program. The base system is just a generic x86 64 image that fit all nodes because this set of instruction is common to each CPU. And I push this image with a tool called kdeploy. Kdeploy is a software used at INRIA in France, which is a very large informatic research entity. And the kdeploy was made for deploying barebone operating system on compute node. Kdeploy takes a compressed archive as an input, and it puts this archive on each node you want to deploy. You have to register the MAC address of the node, and as soon as kdeploy knows the MAC address, he will start a TFTP boot. This is the same as a diskless deployment. Kdeploy put an initramfs on nodes, and each node, each deploying node boot on this initramfs, and as soon as the host is started, kdeploy sends commands to configure the compute node. And the originality of kdeploy is the way kdeploy sends information to nodes. To communicate or to send data with nodes, kdeploy used the communication infrastructure called TACTUC. In most barebone deploying software, it's a loop. You deploy the first node, then the second, then the third, etc., etc. You can do this loop in multi-threaded way, where you deploy the 10 first node, then the 10 following nodes, etc., etc. But it remains sequential. With TACTUC, when you send data to two nodes, these two nodes resend the data to two other nodes. So it's a kind of hierarchical diffusion of the information. And this communication infrastructure relies on SSH. So you can deploy, you can send information on computer that are not in the same LAN domain. They can be on different IP network. So kdeploy is a bit original because of this. And it's a super lightweight deployment tool because it only orchestrates existing services such as ESC, DHCP, pxboot, grub, etc., etc. kdeploy is only a communication layer between all these existing services. To make the post configuration, we use Ansible. Means that as soon as the operating system is deployed on compute nodes, we used Ansible for post configuration. Ansible is super useful because in Ansible, you have to make an inventory of all hosts, and you put this host in a group, and you can attach a succession of roles with all this group. A role is a set of tasks that must be performed on the host. For example, you can have a role LDAP client to link your compute node with the directory service, such as OpenLDAP. And this role, LDAP client, contains several tasks that enable your compute node to contact the LDAP server. You put the certificate for the SSL connection with the LDAP server. You install all required packages, such as a SSD, LDAP client, and things like that. You set the good ownership and permission on some files. You write the configuration files, etc., etc. You have a lot of tasks attached to the LDAP role, and this LDAP role is linked to some group of machines. And when you want to apply your Ansible playbook to hosts, you launch the Ansible playbook command, and this command make a loop on all defined hosts and apply the configuration you define. Like a common barebone provisioning software, this is a loop. This is a sequential loop that can be multi-threaded, but it's sequential. So during the life cycle of the HPC cluster, you have to upgrade. For example, when you add a new software, when you have to upgrade packages, when you have to upgrade distribution or drivers. So you need to manage all nodes at once. We don't connect to each node and run command in a sequential way, but we have to broadcast commands or files on the whole cluster. There is a lot of tools that can do this. A lot of multi-threaded tools like cluster SSH, or I think the most famous in HPC environment is PDSH. But we have really a lot of tools. On Maggie, we use a tool called Cache, and Cache also rely on tactic infrastructure. So I can broadcast command in the same hierarchical way as I deploy my images on my HPC cluster. And what is a bit original in Maggie is that we combine Ansible and Cache to make Ansible distributed and broadcasted. So when I need to make an upgrade on configuration on Maggie, instead of running Ansible on my host and make the Ansible master connect on SSH to each host to apply configuration in a sequential way, I order to every node with a cache command. So I take advantage of the tactic communication infrastructure to broadcast my Ansible playbook on each host, and I order each host to apply their own Ansible configuration. It means that you don't have an Ansible master that deploy a lot of nodes, but you run the Ansible master on each node to configure itself. So it's a fully distributed application of the Ansible playbook. Now we will talk a little bit about software management, because as I said before, we have a lot of architecture of CPU. So software management is really a subject for us. You should know that by default, when you install a program from a package manager, all these programs are compiled for regular x86-64 architecture. So you don't have optimization. If you have a very top-notch CPU, you don't care. You don't get a set of specific instructions. That's why on HPC computers, we compile software from sources. You have a lot of compilation tools. I think you know Make and CMake, but you also have Meson, and really you have Ninja, you have a lot of compilation tools. And the advantage of compiling software from source is to have the software tailored for your CPU. But when you have a lot of CPU architecture, you have to maintain several instances of software. And you have to also to handle with several compilation configuration. So you have a kind of matrix of complexity with the potential compiler compiling tools and the architecture. So you realize that it can be a bit tricky. And compilation of HPC tools can be very cumbersome because sometimes you have to explicitly points on libraries, and you have to fix some environment variable. So when you're on the process of compiling the software, you're very aware about all this stuff. But when you didn't touch the application for years, and you must recompile the application mainly for upgrade sake, you have to remember how you compiled this application. Notes may not be up to date, so it's a bit complicated. That's why also for software management we use Ansible, because you're forced to write the playbook to compile your software, and the way Ansible is designed, it's very easy to adapt on this or this compilation tools. And roughly speaking, my compilation is a role for the software. For example, if you want to use Sage, you have a role Sage, and this role is invoked in a task that is a loop on all CPU architecture. So I run the compilation one time, and a loop is triggered that compile the software for each CPU architecture. I didn't talk a lot about the cluster backend, but what we call cluster backend is all system services that are required for the good working of the HPC cluster. So all these services are really frugal in terms of resources. So they are good candidates for containerization. Instead of having a lot of process running on the administration node, we can do containers to separate them and have something clean, because you can move containers easily from one host to another. You can snapshot and backup are really easy. So that's why container is a good thing. But one service is equal to one LXA container. In an HPC cluster, you have services like DNS server, OpenLDAP directory to store users, a mirror if you have your own local distribution mirror, and you also have the monitoring nodes, etc., etc. Kdeploy itself to deploy nodes. You have a lot of services, but these services must be treated as a comprehensive operating system. It means that you don't containerize the program itself, but you containerize the whole userland of operating system that host the service. It means that you containerize systemd and not the service itself. That's why we use LXC instead of Docker or Podman or other container engine. And to finish, the way Maggie is administrated, the backup are very, very easy because all our configuration are in Ansible playbook. It means that when you make a push of your Ansible playbook, a dump of accounting data are your job, how many resources you used, your accounts, etc. You also make a directory of LDAP because it's all your user account. So you should back up them. And the metrics, because I have people that work on energy consumption of EA workflow. So metrics variable are very valuable for us. That's why we back up them. So it's a small shell script of 10 lines to back up my whole HPC cluster. And in system administration, backup should really be easy because when you recover, you're always in hot water and you don't have time to read a script or a script nested in other scripts that are nested in other script, etc., etc. You have to keep things very simple. This is the ending word, keeping things very simple. So I thank you for your attention, and if you have questions.
Okay, thank you very much, Nicola, for this nice presentation. So, Safa, sorry, I missed your question. Can you please ask again your question because so Safa said, does it also help when adding a new node? But I don't understand in which
Sorry,
part you asked this
I,
question.
I don't hear the question. I didn't hear.
So Safa said in kdeploy, does it
Mhm.
also help when adding a new node?
Yes. When this is a good question. I didn't talk about hardware upgrade, new nodes. When I receive new nodes, I declare the MAC address of the node, and I have an Ansible receipt that add this node to the deployment, skdeploy, to create an entry for the DHCP server to be able to send the init ramfs to the node when it's deployed. And it also upgrade the DNS server to have a entry for the host. And I think it's all. Oh, I don't remember, but yes, when you add a new node, there is an automated procedure to declare the node on kdeploy. And then when the node is known by kdeploy, I can run the deploy command to start the node, to deploy operating system on the node.
Okay, thank you, Nicola. So I have a question, Nicola, about the tools. For example, since you have heterogeneous nodes, so when you install, for example, I don't know, GCC or something else,
Mm-hmm.
so you remove all the optimization, the architecture optimization, or you still keep them.
It depends on software. There are softwares that are not really closely related to the CPU architecture. But for example, GCC does not really care about the CPU architecture because you can specify to GCC for which architecture it must compile programs. This is with the mRch option. And this cross-compiling. But for other application, let's say Sage, for example, mathematics software, with Sage, it's important to have an optimized compilation. And for this kind of software, I have several flavor of the application, but they're separate in terms of file system. You have a directory where I have all my program, and in this directory, you have Sage for EMD processor this generation, Sage for EMD processor another generation, for Intel with Haswell architecture, and each application has a flavor related to the targeted CPU architecture.
So as many architecture, like different architectures you have, you need to install like. Okay,
Yes,
I got. Okay.
yes, yes,
Yeah.
yes. You have to make a compilation for each architecture. Hmm. That's
Okay,
why
I got.
I called it automated way, because with Ansible it's a loop. It's only a loop where I define the architecture and it compile regarding the architecture. Okay.
Okay, so like since I'm using Easy Build, so I just like switch off the optimization to make it easier. So yeah, but I know it's not a good idea
And
to do that.
you can really enhance performances with instruction. I have a very spectacular feedback from VASP users. Without any optimization, it take a time n, and it with optimization it was 30 uh, 30 times more fast.
Yes, yes. If you compile only, for example, if you take like C code and you
Mm.
compile it with optimization and without, you can see the difference. So yeah.
Mm.
Uh, so Safa said, what kind of jobs do you usually expect on the cluster?
Oh, the scope is super large. I have, let's say, classical jobs like Sage, VASP, GROMAX, a lot of regular HPC tools, HPC programs. But we also have home written programs, home design programs. I have some people that do parallel computing at University of Southern Paris North. So we have people that develop code on Maggie. So we have a mix of production users and developers on the same machine. So they must share the same node, which was a bit cumbersome in the early days of Maggie. And I have people that make network simulation, for example. I have some people that run simulators, network simulators. I have people that only run jobs to measure the energy consumption. So really, we have a lot. We have a lot of different people on Maggie. But the most difficult to handle is mixing production people with development people. That's why I started to move development people in virtual machine. These virtual machines are compute nodes; they're configured the same way. But people can are alone on the virtual machine and they can develop bypassing the job scheduler, because when you develop, you don't want to wait hours to run just a test job to see if your program works well.
Okay, thank you. So I have another question. So So I have started to work with OpenHPC with one of my students. I don't know if you think it's a good idea to use OpenHPC. It's like gather all like the tools that you mentioned in your presentation, or it's like better to implement one by one by yourself.
It's really hard to say. OpenHPC is a super good tool. That makes things clear. It's a very good tool. Like Bright Cluster Manager, like Rocks, like all these tools are really good. But um, it depends on how many people are assigned to your HPC cluster for administration. They're easy to deploy, they're super fast, it's intuitive to deploy nodes. Because sometimes when you have to operate kdeploy, this is hard. You have to dig in the source code of kdeploy to understand things because it's only used at INRIA and the University of Sorbonne Paris North. So we don't have a lot of users. At INRIA, it's really used because it's a deployment system for the slices infrastructure. So it's a very large European infrastructure. So there's a lot of people, but inside the INRIA. We are the only site outside of INRIA that use this product. So you have to dig in the code to understand things. You must. It will cost you time to maintain an heterogeneous software stack like Maggie. And the other problem is there is only one person that know how this stack is managed. With tools like OpenHPC, it's a very used tool, so there's a lot of people that know about OpenHPC, and so it's easier to maintain, even if in terms of people, of administrators. So I prefer my way of doing things. It's obvious, but this is not the way to do things. There's a lot of variable to answer this question, and but I think where my solution is interesting is when you have a lot of different users, because sometimes I have users that ask me to have the same as Maggie on their laptop to develop. In this case, I only have to give them the Ansible receipt. They applied it to a virtual machine in their computers, and they can work as if they were on Maggie. They can develop their code. They can try with Maggie libraries. So it really depends on what you do. Um, if you have, let's say, a production HPC cluster like yours in Morocco, OpenHPC is a good solution because it's robust. It's deployed in a lot of sites. There's a community with OpenHPC. Tools are packaged for it. So for production cluster, it's good. But when you have a cluster look like the Faucon Millennium in Star Wars, maybe a more flexible solution is an asset. It really depends on what you're doing.
Okay. So you mentioned the Bright, but Bright now is very expensive. So
Yeah,
Nvidia
far too
bought it, and
expensive
yeah,
for.
yeah. Okay. Okay, thank you very much, Nicola. I don't know if you, so the audience have another question. So if not, I really appreciate the presentation, and thank you again, Nicola. And
Thank you for your invitation, Imad. Thank you.
see you soon.
See you soon. Bye bye.
Goodbye. Goodbye. Thank you.